Alrighty guys, so after combing through the curriculum yet again, these are the things that I need to expose you to so that they're not new to you tomorrow or Wednesday or Friday. So that's what I'm doing. Okay, I'm going to start off with accumulation functions. And I want you to know that the accumulation is defined by this. Accumulation A for accumulation function is equal to the integral from a to x f of t dt, where a is a fixed number and x varies. The lower limit, a again, is fixed. This thing up here can vary to anything, any number. And the assumptions are is that f has to be defined such that this integral exists for all x in a closed interval. So I'm not going to get into the nitty-gritty of it because we don't have time. We'll do it later before the AP exam. But what happens is that you integrate this function f and you get a new function which we call a of x, and a of x is just evaluated by accumulating area underneath a curve. Okay, a couple of quick notes. So I already did this and I made a mistake, so I had to delete the video. The integral from a to x f of t dt is equal to the opposite of the integral from x to a. So if you want to swap your limits of integration, you just swap them and multiply your integral by a negative. And what I was saying, which I said correctly, but I accidentally hit my mouse and stopped the video. Sometimes you'll get these weird integrals where the limits of integration are backwards. And when that happens, just flip them and multiply by a negative because these two things are equivalent. Okay. The other thing is an integral from a to itself of a function is 0. Why? Because we're talking about area under a curve, and the area from something to itself is non-existent, so the area would be 0. Now I'm going to go to page 308 in the best book, alright, and I have a little side note here which I'll talk about when we get into the calculator aspect of it, because I was using my newer TI and then I went to this TI because I like this calculator better, and it's in math mode and I can't get it out of math mode for some reason, and so anyway, I didn't know how to put this into those calculators in math mode, so I had to relearn that. So I put a note to self. Okay, so page 308. Alright, and so here's a function, a velocity function, velocity versus time. And what we learned is that if we compute the area below the velocity curve, we get distance traveled, right? So what we can say is that distance is equal to the definite integral from a to b of velocity, v of t dt. We know this, right? And here's a graph of velocity, okay? Kind of, very geometrically shaped, which is nice because that's going to help us a lot. Let me get a pencil because I'm going to be writing in this book. We want to find the distance, in the first t seconds, for example. So how we can denote that is that the distance is equal to the integral from 0 to t. We might want the first second, we might want the first 2 seconds, and so forth. And what we know is that our interval goes from 0 to 5. Okay, so this is what you do, or how you can think of it. You can think of, the velocity from 0 to 0. Well, I'm sorry, the area from 0, 0, the distance. Well, at 0, we're not going anywhere. So the integral from 0 to 0, the distance, right, of this function is equal to 0, because we just learned that the integral from a to a of a function is 0. Okay, so in the first second, we might want to compute, how far did this thing, whatever it is, move, and this object. So we can compute d of 1. Well, that's just the integral from 0 to 1. And as you can see here, this is a little triangle, and it has this side length is 1. And when x is 1, the height is 2, so 2. And we know from geometry that the area of that triangle is 1/2 base times the length. And so the area of this little triangle turns out to be 1 meter. Now, we might want to figure out the first 2 seconds. So I got to adjust my camera here because the book's hitting the base of my elmo, so sorry about that. Well, I already know this is 1, right? Because I computed it here. So all I really have to do is compute this little rectangle and then add it to the 1. So if I compute the area of this thing here, I've got 1 times 2 is 2. And if I add 2 and 1, I get a total of 3 meters. So over the first 2 seconds, this object went 3 meters. Okay? And I can continue on. I can do this one here if I want to, right? So I can do d of 3, which is the integral from 0 to 3. Well, we already computed the first 2 seconds. So again, this is a little trapezoid. And it has a width of 1 and a height of, let's just say, 2.5. And we know that the area is equal to 1/2 the height, which is 2.5, times the sum of the bases, right? So anyway, we can keep going on and on with that. And if we do, for each input, we get a new output, we can actually make a table of values. And here they are for this particular function. And if we graph these, we get this picture here. Okay, so, you know, at time is 0, the object's gone 0 meters. At time equals to 1 second, the object went 1 meter. After 2 seconds, it went 3 meters and 5.5 meters and so forth. And we can connect it with a smooth curve. Okay, and here is the original velocity graph. And it says right here, you know, in comparing the graphs of velocity and the distance function, so this is distance now, right, because we were computing the area, we were accumulating the areas under this curve to get this function. We got a new function, namely distance, from velocity. All right, now our calculators can do this, and it's slow, but you're going to have to do it, say, for a free response question on the AP exam. You may have to do it for maybe one question here, but I think on the semester exam, they're going to have you actually compute the derivatives of these things more than, you know, coming up with a graph or whatever. So I wanted to show you how to do it on either the CE or this version of the TI. So here's an example here. Using a calculator to graph an accumulation function, it says let f of t equal to t, a equals to 0. Use fnint to graph this function here. Does it have a simple formula? Well, I know if I integrate this thing, right, if f of t is t, if I integrate this function from 0, a is 0, to x of t dt, then what I'm going to get is t squared over 2 from 0 to x, which is going to be x squared over 2, right? So that's my distance, right? Remember, the antiderivative of velocity is distance. So if we go into y equals, you're going to have to put this in terms of t, which we had to before anyway. It's just in this format. It was a little bit weird to me. So what you're going to do is you're going to press, so I'm going to do it in y1. You're going to do math 9, which is fnint. So if you do math and you scroll to 9, you see it says fn. Oh, I'm sorry, you cannot see that, can you? I apologize. If you press math and then scroll to 9, it's fnint. All right, and you press enter. Oh, math 9. And then this comes up, right? And what we want to do is we want to go from 0 to x, just like, you know, you see in the formula for the accumulation function. The difference is my function here is t, right? So you're going to have to use the alpha key, alpha t, and put your t in, and then you're going to differentiate with, integrate with respect to whatever. This is always going to be t, so with respect to t, so you're going to use your alpha key again. And when you hit enter, I'm going to shut this other one off because I already hit the graph key to make sure it came out right. Remember, when we integrated over here on the side of the page, I got x squared over 2, a parabola, right? 1/2 x squared. And lo and behold, there's our parabola. So this is the accumulation function for the function f of t equals to t. We'll talk more about it tomorrow or something. What I really want to get to is the nitty-gritty of this thing. And by the way, and I'm not going to go into this right now, but some of you may know, and I actually used to always graph these in parametric mode. This makes it a little bit faster to graph the accumulation function, but not by that much. So, you know, whatever floats your boat. If you want to learn parametric mode before the test, you can do that. I'm not going to cover it right now because, again, I don't think you're going to really have to graph them. I think you're going to have to perform some operations with the accumulation function. So, that being said, we get a new function, right? Called the accumulation function from a function f, which is a rate of change function. Okay, so now that we have this accumulation function established, what I want to show you is that the derivative of the accumulation function is just equal to f of x. This is really cool. Okay, so for instance, if f of x, and you notice I'm using a different f here now, which again is just notation, it's no big deal, but if f of x is equal to the integral of 1 to x t squared dt, and we want to find the derivative, what we're doing is we're taking the derivative of an integral, and the derivative is the inverse of the antiderivative, or vice versa. And so when you take the derivative of an integral, these two sort of negate or cancel each other out. The thing is that what's going to happen is whatever is in here, you're going to get x squared. Here's the reason why. If I integrate t squared from 1 to x, this is a simple integration, I get t cubed over 3, and then I have to evaluate it from 1 to x, right? And when I use the fundamental theorem and plug the upper bound and the lower bound, I get this function right here. Well, if I integrate this function, if I take the derivative of this function, the derivative of this thing is just, you bring the 3 down, the 3's cancel, you get x squared, and the derivative of a constant is 0. So you get what you started with, except this is a t and this is an x. So when you integrate these things, all you do is take what's inside and replace the t's with an x. It's that simple. Alright, so let me just do a little side one here. So let's just suppose we have the integral from 0 to x of, I don't know, t squared plus 3t minus 1 dt. And I wanted you to find the derivative of this. Well, the derivative would be x squared plus 3x minus 1. Wait, yeah. Okay, all I'm doing is taking the function in here, and for every t I'm replacing it with an x. That's it. Okay, so here's a good example here from the book. If g of x equals 1 over x, 1 to x, 1 over t squared plus 1 dt, find the equation of the tangent line at x equals to 1. So the first thing I want to do is I want to take the derivative, because I need to find the numerical derivative, because that's going to give me the slope of my tangent line. So I know the derivative of this thing is just 1 over x squared plus 1. Again, all I'm doing is taking this integrand and replacing it with x. This is my derivative, so now if I plug a 1 in, I get a slope of my tangent line at 1/2. The other thing is that I want to evaluate this thing at x is equal to 1. So if I evaluate the original integral at 1, I have the integral from 1 to 1. If I'm plugging in a 1, I get out a 0, so I get the point 1, 0. Now I have a point, and I have a slope, and so I can use the point-slope formula. Y is equal to 1/2 x minus 1. There's the equation of my tangent line. The other thing you're probably going to see, and I saw a couple on your review, was the use of the chain rule with accumulation functions. So you're going to know that you have to use the chain rule when you have weirdness going on in the upper bound or lower bound. You could switch it to the negative of and swap the bounds if you need to, but the x should always be on top. And there's all kind of scenarios where this could happen, but a simple one is we have this function right here. Okay, 0 to x squared sine t dt. And remember that the chain rule is derivative of the outer function recomposed with the inner times the derivative of the inner. So what you do is you always let the outer function, and I just call it a different name, I call it capital F of x, always let the outer function go from the lower bound to x, always, because that's the definition of the accumulation function. So in this case our function is sine of t, so I plopped my sine of t in there, and so the derivative of that is just going to be the sine of x, right? Because with this stuff going on, I can't just plug this in there like that and say my derivative sine x squared. That can't happen. This is composite. So you rewrite it like this, take the derivative, which is just the sine of x, and now remember chain rule says take the derivative of the outer, we did that, recompose it with the inner, So I did that here. The inner was whatever's up here, x squared, times the derivative of the inner function, which is 2x. So generally we let this thing up here be our inner function, or we call it g of x. And this whole thing here from 0 to x will be, and by the way, the lower bound doesn't matter. If there was a 3 there or a 5 there to x, it doesn't matter. The derivative is still sine of t. Sine of x. Here's another one. Let me move this book because it's getting on my last nerve. And I haven't been paying attention to what's on the screen, so I hope I didn't mess anything up here. Here's another one. We want to find the derivative. And again, you see this just goes from 2 to x squared. So I put this one in here. I know this is the same as the last one. Function's different, but I just want to show you that that lower limit doesn't matter. So anyway, what's the outer function? The outer function is going to be from 2 to x. Okay, so you leave the lower bound alone because that's fixed, whatever number they put there. But the upper number you're going to say to your grader, on the AP exam anyway, the upper bound is x. And you want the derivative of this thing, so the derivative is just x squared plus 1. So you took the derivative of the outer. The inner function again is x squared, so its derivative is 2x. So according to chain rule, we're going to have derivative of the outer. Now if I recompose that with the inner, I'm going to plug x squared in for every x. So that's going to become x squared squared plus 1 times derivative of the inner function. And then just cleaning that up a little bit, there's your derivative. In the next example, it's not any more complicated, but it's got, you know, a much different upper bound here. So the outer function is f is equal to 0 to x sine t dt, which means that the derivative is just the sine of x. The inner function is 2x plus 1, so the derivative of the inner function is 2. Putting this together using chain rule, I say the derivative of the outer recomposed with the inner times derivative of the inner function. And I wrote it nicer down here. Here's one more. I think this is the last one. Integral from -1 to root x tan u du. Okay, so the outer function is going to be from -1 to x tan u du, so that derivative is tangent of x. The inner function is the square root of x, and so the derivative is 1/2 x to the -1/2, right? So again, using the chain rule, derivative of the outside, I've got to recompose this with the inside now, so it's tan root x times 1/2 x to the -x squared. And if I clean that up, you know, I can bring that negative exponent downstairs and rewrite it as a radical. So it's tan root x over 2 root x. Pretty nifty. Okay, I know I covered area between curves, or I think I did. Maybe I didn't. I know I covered area in the plane, but I don't know if I got to 2 curves or not, so I just want to say it in case I forgot, because time has been crazy. I just want to say this. So far, we've been working with area between a function and the x-axis, you know, like, I don't know, x squared from 0 to 2 or something like that, right, when we revolve it and whatnot. And I know that you have had a couple of examples where you had little things like this that you had to revolve around an axis. So, the formula to find the area between 2 curves. First of all, the intersection points are the limits of integration. And you can find those by either setting the 2 functions equal to each other, or if it's a calculator problem, use second calc intersect in your calculator. But the area always goes top curve minus bottom curve, always. In this case, f is the top curve because it's some kind of a, you know, maybe it's -x squared or something like that. And g is below the top of that, so it's the bottom curve. Okay, so in general, it's always going to be top curve minus bottom curve for area between 2 curves. I made a little note here, you know, set your functions equal and solve for x to find your limits of integration, or use a calculator if you need to. Okay, but the thing is that, you know, these areas are not hard to find. I'm going to get the book again. But something of importance that you might see on the exam, which we need to cover, is where we have area in various regions. So in other words, we have more than 2 points of intersection. So for instance, I think I did this one in class, but I'm not sure. So let me just get out my pen here. We want to find the area of the region bounded by f of x. So this is an example. F of x, equals 4x minus x squared, and g of x equals 5 minus 2x. Okay? So I know this is an upside down parabola, and I know this is a linear function with a negative slope. And what I know is if I were to sketch, a quick little picture of this thing. Now let's see, if this is 0, so negative 4 over 2a, so it'd be about 2. So this thing's going to go something like this. It's going to be this little region here. Alright, you can graph it on your calculator. But anyhow, the idea is I have these 2 points of intersection that I need to find because those are my limits of integration. So all I have to do is set my equations equal. 4x minus x squared equals 5 minus 2x and solve. So, if I add 2x, I'm going to bring this over so my x squared is positive. So I'm going to have x squared. If I add that plus 6x minus 5 equals 0. So I'm going to have x, this is not going to work, is it? Did I do that right? Wait, I'm sorry. My bad. Plus 5. Now it'll work. So x plus 5 times x plus 1 equals 0. So x is equal to negative, what am I doing? I'm sorry. Hang on. Miss Wilson can't add. Alright, let me start over. 4x minus x squared equals 5 minus 2x, right? I'm going to bring x squared over. So I have 4x is equal to x squared plus 5 minus 2x. I want to be careful because I don't want to make the same mistake twice. So we have x squared minus 6x plus 5 equals 0. Okay. So that's going to be x minus 1, x minus 5 equals 0. So if I solve, x equals 1 and 5. So my limits of integration are 1 to 5. What I know is that my area is equal to integral from 1 to 5. Now all I have to do is get my integrand here. Well, it's top curve minus bottom curve. The linear function is the bottom curve. So it's going to be 4x minus x squared minus the bottom curve, 5 minus 2x dx. And I'm going to clean this up. This is the integral from 1 to 5. So I have 4x minus a minus 2x gives me 6x, right? 4 plus 2 is 6x. Negative x squared. Okay, now if I integrate this thing by hand, and I'm going to do it, I'm going to have 6x squared over 2 minus x cubed over 3 minus 5x from 1 to 5. I just want to see what I get. I'm going to have 25 times 6. Well, 25 times 3, right? 2 goes into 6 3 times. So I'm going to have 3x squared minus x cubed over 3 minus 5x from 1 to 5. I'm gonna move over here. I need more room. So if I plug in the 5, I'm going to have 3 times 25 minus 125 thirds minus 25 minus, now I'm going to plug in the lower bound, so 3 minus 1/3 minus 5. So this is 75 minus 125 thirds minus 25. And 75 minus 25 is 50, so I'm going to write that as 50 minus 125 thirds minus, now in here I'm going to have negative 2 minus 1/3. So I'm going to have 150 minus 125 over 3, which is going to be 25 thirds minus, now here I'm going to have negative 6 minus 1 is negative 7 thirds. And that's going to become a plus. I'm going to check my answer here. 25 and 7 is 32 thirds, and that's the answer. Whew. So I did it a little bit messily, sloppily, sorry. Now let's use the calculator for this. So let me get rid of these accumulation functions here. If I want to let my calculator do the work, it's really easy. Okay, all I have to do is come up with my limits of integration and what my integrand is, and then I have to put it into my calculator that way. So my integrand is 6x, so I'm going to put this in on the side and then I'll show you. X squared minus 5. Okay, so I put the function in the calculator and I'm going to hit graph. And now I'm going to do second calc 7 for the integral, right? From 1, enter, 5, enter. What it's going to do is shade that region in, and we get about 10.7, right? So is 32 thirds 10 sevenths 10.7? Yep, get the same answer. Okay, so again, you have to be able to get this written down and then let your calculator do the rest of the work. So you're going to have to do some work. The other thing you could do in your calculator is you could put each function in individually. So let's say 4x minus x squared in y1 and 5 minus 2x in y2, and hit graph. And there's the parabola, and there's that. Okay, and then again, you know, this is the region you want the area, so you're going to have to go ahead and do second calc 5, which is the intersect feature, and you know, you go close to a point of intersection you're interested in, just hit enter 3 times, and there we get when x is 1, y is 3, so x equals to 1 is the first bound, and then you would do it again, second calc 5, and just arrow closer to that other point of intersection and do enter, 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 and the other x coordinate is 5. So there's your limits of integration. Now if you try and do a second calc 7 on this, you're going to have a mess, because it's going to take area above, area below, and as you can see, that's nothing like the answer that it is. Okay, so that's why we have to get it cleaned up and put that into our calculator that way in order to do that. And you know, you can do that in the calculator too. In y1 you could put this just like this and then hit the graph key and do second calc 7. You get the same answer. Okay, so we'll do some more practice during the week. You're being exposed to it, so that's my main concern. Okay, this is just a picture I pulled offline because it was easier. A lot of times curves, I'm going to just change my seating here. A lot of times curves, when they intersect at more than 2 places, like you see here. And you're going to evaluate it the same exact way, but you have to be cognizant of the fact that from this interval from 0 to 2, the area from 0 to 2 is going to be big curve minus little curve. Now I don't know what f is, and so this curvy one is g and f is the linear function. So in this case it would be f minus g dx. And then you would add to that the integral from 2 to, I don't know what this is, so I'll make it up, 2 to 4, let's say. And now g becomes the top curve and f becomes the bottom curve, so it would be g minus f. Big curve minus little curve dx. Okay, you'd compute this, get your area for that region, compute this, get the area for this region, and then add them together to get the total area. Okay, and again, you can graph each one individually on your calculator and do second calc intersect to find those points of intersection, and go from there. So same thing, just more than 2. I was asked to talk about the squeeze theorem. It's in the curriculum, so I'll talk about it briefly. I mean, it's really kind of easy. And again, I found a picture online that I just printed real quick and then colored it up. So squeeze theorem, aka, is also called the sandwich theorem or the pinching or pinch theorem. What it says is this: you know, if you have 2 functions f and g that squeeze together at a particular point, and then you have some other function h that's in between f and g, okay, so h is between f and g. It says that when you take the limit of f, if it equals the limit to g, then the limit of h has to be the same. Here's the picture so you can see. So I used a marker to color it up. This L is the limit, the height, right? So F is the green one and G is the purple one. And I have some function h in between those two. If the limit as x approaches a from the left and the right, they have to, both sides have to be the same in order for the limit to exist, is L. And the limit as x approaches a from the left and the right of g, or limit as x approaches a for g, is L. If this function is in between, it's going to be compressed into that same limit, that same height. So that's essentially what the squeeze theorem says. Algebraically, an example would be like this. You have some function. This is a negative 1/3 x squared plus x squared minus 7/3, and g is the cosine of pi x over 2. They want you to find the limit. Maybe this should have been cubed. Yeah, this should be cubed. So find the limit as x approaches 2. Okay, what I know is that f is given and g is given and h is some function in between. I don't know what h is, but it doesn't matter what it is. When I take the limit for f, I have, negative 1/3 times 8 plus 4 minus 7/3, and that cleans up to a negative 1. And when I plug a 2 in for g, right, I get pi over 2 pi over 2, which is pi, and we know that the cosine of pi is negative 1. The limit of f equals the limit for g. If h is in between f and g, then the limit as x approaches 2 for h also has to be negative 1. That's the squeeze theorem. I'm not going to harp on it because really no other reason why we should. Another quick thing, the average value of a function. So this was all in chapter 6 of the best book, where the accumulation function started. Average value of a function is really kind of cool, and I'd like to talk about it a little bit more, but right now we don't have time. If f is continuous over an interval, then the average value of f on that interval is just 1 over b minus a times the integral from a to b of the function. That's it. What I have to do is take 1 and divide it by b minus a, and then multiply it by the integral, and you're golden. So, example, find the average value for this function over that interval. Well, it'd be 1 over 2 minus 0, b minus a, times the integral from 0 to 2 of that function. And if we integrate this function and then multiply it by that 1/2 sitting outside, we get 1/3. And what that means is that there's going to be a rectangle of height 1/3 that passes through that point on the actual function. Again, don't worry about that part. We don't have time right now. Alright, that concludes this video. This is, I guess you can kind of call it a chapter 6 video. We'll talk about it this week. Have a great day.